our physical sciences session. My name is Themba Ncube. Today we are focusing our attention on exploring, the kinetic molecular theory of matter to try and understand, what exactly happens at a very microscopic level and try to link that with what we exactly observe, when, a change of phase takes place within the three states of matter, which is the solid, liquid, gas. So we'll look at this actually, in terms of the physical properties of materials within the broader section of matter and materials. Right. Having said that, so we want to also appreciate that our focus is on the kinetic molecular theory, okay, of matter, to try and explain, in terms of why, matter behaves in the manner it does under different, conditions, and why, solids, liquids, and gases, have got different properties altogether. So this relates actually to the physical properties of materials, right? Okay, so what's the thinking that's going to guide our discussion for today? The big question that we want to ask ourselves is that what evidence, because science is purely based on, empirical evidence. So we are saying what evidence is there for the idea that matter consists of particles. But this is, in the backdrop or, on the background, we understand that matter is anything that has got mass and it occupies space. So the big thinking that we have today is that what exactly suggests or what evidence is there for us to really say that indeed matter consists of what we would call, particles, right? Okay, so that's the big idea. Keywords in terms of the terminology. One also has to remind ourselves that, okay, remember, the language in itself is located within the context of science. Now, so in physical sciences, our definitions, terminology is either we know or we don't, which is based on our remembering skills. So what is our point of reference for what is actually acceptable in terms of definitions will definitely be our examination guidelines. So what are the keywords that will, be used quite often in our discussion for today? The key terms are diffusion as well as Brownian motion. So Brownian motion is actually capital letter B. Why? Because it was named after, a scientist, so it's somebody's name. Hence, we'll call it the Brownian motion. Right. Okay. So what is diffusion? Diffusion is the spontaneous movement of particles from an area of high concentration, okay, to an area of low concentration. So these particles are actually in constant state of motion, right? And then during diffusion, what happens? Particles move from a region where there's many of them to a region where there's very little of them. And then that suggests something, as we are going to discover, about the nature of matter in as far as the kinetic molecular theory, right? Okay, so practical examples of diffusion, because diffusion is about the movement of particles from a region of high concentration to a region of low concentration. What are some of the, everyday life examples? So if we add, let's say, for example, a food colorant in a beaker containing water, what is it that we would observe? We would observe that, the color will spread, gradually throughout the whole, so to give us a uniform color at the end of the day. So that's a practical, observation in as far as diffusion is concerned. What about the smell of air freshener filling up a room? So what you'd observe in real life, you get into a room, you stand by the door, you spray, let's say, an air freshener. After a couple of, seconds, the person sitting right at the corner will observe the smell. So it says something about the movement of the particles. But our focus today is precisely to try and bring an understanding to say, at a microscopic level, or from a microscopic view, what is happening in terms of the particle. But remember the big question that we asked in terms of the evidence to say that matter indeed consists of particles. Right. So these are the practical examples in as far as diffusion. Right. Okay. Right. Now, what can you deduce about the matter, okay, about the behavior of matter, that is, from the observation of diffusion? So this is the question. So science, in many ways, in its very nature, it's about us asking questions, and the questions that we pose actually, must be accompanied by a certain way of thinking, okay? So for us to arrive at a conclusion, there must be supporting evidence. It is the inquiry, nature of science. That's how science is all about. Hence, we always want to focus ourselves about asking a lot of questions. So it's not so much about the correctness of the answers that we give, but also the questions that guide our thinking in terms of understanding, the bolts and nuts in terms of the detail. But our focus today is precisely on, the behavior of matter. Why do we say that indeed matter consists of particles? So we'll keep on, reminding ourselves of the big question as we try and discover some of the very exciting facts about the nature of any form of matter that is, right? Okay. And then, so the practical examples of diffusion, we know that matter must consist of very small particles, okay? Particles can be molecules, atoms, but the word particle is used generally to refer to those units that make up a substance, okay? Now, and secondly, there must be spaces between different particles, okay? For particles to actually move from a region of higher concentration to a region of lower concentration, we are saying that there must be spaces through which these small particles, these minute particles, actually move, okay? Otherwise, the movement or change of position of particles making up a substance will not be possible, okay? So it means there must be spaces, right? We're onto something here. And then it says here, the particles of matter must be moving into these spaces. So there must be motion, okay? Now, already, what do we know? We know that any form of nature, any form of matter actually is in a constant state of movement, okay? So movement, motion, we're saying the same thing, right? Okay? Now, and also these particles have got kinetic energy. Now, the word kinetic energy, very, very important, because it has to do with the energy that the particles have, by virtue of them being in a state of movement or in a state of motion. So a particle that has got greater kinetic energy is moving faster, okay? So that's the link. Those, by comparison, that have got very low kinetic energy, the speed is very slow. But, we are saying that all forms of matter are in constant state of motion. So there is some kinetic energy, be it a solid, be it a liquid, be it a gas, right? Okay. Otherwise, diffusion will not be possible. Now let's look at a practical demonstration of what exactly happens, because some of these ideas can be somewhat abstract, but if we actually get to see and we try and, at least derive some understanding in terms of what exactly happens, okay? So let's look at, for argument's sake, this simulation that shows what exactly happens when diffusion occurs, okay? Right, so these are the particles of a substance, okay? So if these particles are in a state of motion, you'd realize that further to our left, there is a high concentration of particles, okay? Now, these particles, they move across the barrier to a region where they were low concentrated. But one also has to appreciate the fact that, generally, any form of matter has got particles that are in constant state of motion. Okay, so the observation with the food colorant spreading through the water solution, water as a medium, actually, it says that between water molecules, these particles can actually move from one point to another, okay? And for that to happen, it means the particles themselves of the colorant must be in a state of motion, right? Having said that, let's go back and try to understand this in context, okay? But furthermore, we are saying there is more evidence to suggest the particular nature of matter. So when we talk about the particular nature of matter, we are saying what evidence is there for us to really say, indeed, matter consists of particles, okay? Now, this takes us to the next stage, of our discussion, which has to do with the Brownian motion. Okay, so Brownian motion is actually a phenomena or an observation that was made by one of the earlier scientists, which is Robert Brown. You can read more on that to try and understand in terms of the timeline how this idea developed, okay? But what exactly does the Brownian motion entail? According to Brown, or the scientist concerned, the motion of pollen was observed in water. So pollen are these, grains from flowers. So if they were actually put in water, you'd actually realize, because they are colored, you can realize that they actually move through water molecules. So under a microscope, of course, because this is quite microscopic, so the movement could be seen through the water molecules, which suggested that there are some spaces between water molecules, okay? Which suggested that there were some spaces between water molecules, okay? So this is the particle nature of water. And also to say that the water molecules are in a state of motion, okay? So the water molecules are in a state of motion. So this is very important in terms of properties of matter, okay? So they're in a constant state of motion, okay? So a similar observation can be made with when you mix these two substances, okay? If you have, let's say, a glass full of water and then you add some milk, you'd realize the movement of the milk particles through the water. So what does that suggest? It says to us that there are spaces, and again, the water molecules are in a state of what? Of motion. This is something that would collect as evidence in terms of trying to understand, the particle nature of matter with respect to the kinetic molecular theory. Also, if you observe smoke that is, emitted, let's say, from a chimney, the movement of the particles of smoke suggests that within the air there is some spaces, and that the air particles are, in their own right, are in a state of motion. Right. Okay. So the Brownian motion pointed out very important things about the nature of matter, that there are vibrations, which is actually movement of particles, right? Okay. So the vibrations are actually the movement of particles, and then there's this jerky motion that you'd also observe as far as, let's say, smoke as a practical example, something that is, in everyday observation. And then there's also a random change in the direction of movement of particles. So the random changes in direction suggest that there is no order in terms of the direction in which the particles are actually moving. Right. Now, in terms of the kinetic molecular theory, which is the main idea for today, we're saying that this kinetic theory of matter is just a model that explains the behavior of particle, nature of matter. So we want to understand, the nature of matter with respect to the kinetic molecular theory. Remember, the word kinetic suggests something about movement, okay, of molecules. Okay, so this theory is actually a model, just to break it down in terms of what it's all about. So the kinetic molecular theory of matter suggests that all matter consists of particles, right? As we have seen from, diffusion, okay, as well as the Brownian motion, okay? So these phenomena, they actually provide evidence in terms of the particle nature of matter. And again, we're also saying that particles of matter are in constant motion. Okay, remember, kinetics suggests something about the movement. So it means any form of matter consists of particles that are in a constant state of motion. And furthermore, there are empty spaces between the particles. Okay, very, very important. Otherwise, the diffusion as a process wouldn't have been, possible if there were no spaces. But remember, for these particles to move from a region of higher concentration to a region of low concentration, there must be spaces And while there are spaces, these particles in their own right, they must be in a state of motion. Okay, so I think that's how we link the two together. Okay, and then again, the forces that exist between the particles, either attraction or repulsion, as the ones that allow us to have a certain form of matter, taking the shape of the container or having a definite shape. It means there is something or forces that actually keep these particles together, right? Okay, and when it comes to the random movement, there will definitely be collisions between the particles, okay, and the walls of the container. So according to the kinetic molecular theory, these collisions, they don't result in any loss of energy or energy transfer. Why are we saying transfer as opposed to loss? Okay, remember, we know that energy cannot be created or destroyed. In other words, we want to carefully use the word lost energy, okay? Because energy is actually converted from one form to another. So the kinetic molecular theory, what it essentially tells us is that the collision of these particles, because we're saying that this movement is quite random, then if there are collisions between the particles themselves or between the particles and the container walls, these collisions are actually do not result in loss of energy, and we say those collisions are actually inelastic. Okay, and then furthermore, we are saying particles do not possess the same amount of energy. Okay, the amount of energy is not the same. Hence, we talk about the average kinetic energy, which is related to the temperature, right? Which is a very, very important point that we'll try and explore even further. Right. Having said that, so we've managed to look at how diffusion provide evidence relating to the kinetic molecular theory in terms of the fact that all matter consists of particles, and these particles that make up matter are actually in a constant state of motion. So after the short break, we'll try and explore the kinetic molecular theory more into detail. Let's take a short break for now. Welcome back to our second segment. We're still exploring the kinetic molecular theory. So we want to look at some of the evidence that suggests that indeed matter consists of particles, and that these particles are actually in a continuous state of motion. So this has to definitely do with the physical properties of materials, but we want to explain them with respect to the kinetic molecular theory of matter. Right. Okay, now the three phases that we want to appreciate that in matter actually exist in any of those three, which is actually the solid, the liquid, and the gas. So this is in terms of the classification of the three states of matter, right? Okay, so what are some of the properties of a solid that we need to remind ourselves that have got a direct link to the kinetic molecular theory? Is that these solid materials consist of minute particles. Minute means very small, tiny, but the difference will, it depending on the substance of how small. Some particles can be very small, some may be slightly bigger, but over and above, we're saying that all forms of solid, as a state of matter, consists of very small particles. All right, okay. Now, and secondly, we are saying there are small spaces, microscopic, okay, hence these solids are incompressible. Now, if there was, a lot of space, it means we can be able to push these particles together, which would actually change the packaging. So we are saying because of very small spaces, present between the solid particles, they are incompressible. So compressing actually involves, applying pressure to a material such that its shape could change. It can become even more compact. But because of very small spaces that are present, between the particles that make up a solid, then it's not actually, possible for us to compress a solid. Hence, we would say a solid is generally incompressible. Okay, and also the particles of any solid material, like any form of matter, is in constant state of motion. Then these particles, they vibrate. But what does that tell us? It tells us that particles are in a state of motion, okay? Particles in a constant state of motion, okay? But this movement is restricted between the particles because there are smaller spaces, so they are closely packed, okay? So this suggests something about the kinetic molecular theory. It says that these particles are in a constant state of motion, but the extent of motion is just restricted to a vibration, right? And then also in a solid, what is very important or is apparent is that there are strong forces between these particles. This actually ensures that the shape of a solid is actually fixed. So when shape is fixed, what do we mean? We're saying that the shape does not change. So there is definiteness of the shape of a solid. Why? Because small spaces. Why? Because these particles are closely packed. Why are they closely packed? Because there are comparatively stronger forces that exist between the particles of a solid, okay? So these particles, they vibrate within fixed position, and in most cases, they form what is called a crystal lattice due to these strong forces that exist between the particles, right? Okay, now let's focus our attention on a liquid. What are some of the important properties or characteristics of a liquid form of matter? Okay, these they also consist of minute particles. So there's something consistent from a solid to a liquid in the sense that in both forms of matter, the composition is such that these forms of matter are both consisting of what? Minute particles which are small. So it suggests something about the particle nature of matter, which will obviously link us to the kinetic theory of matter as a model, okay? Right, and then what about spacing between the liquid particles, okay? The spaces are slightly greater. So when we say slightly greater, this is by comparison to a solid, so it's relative. Hence, they can be compressed slightly. So liquids can be compressed to a smaller extent. Why? Because the spaces available between the particles is comparatively greater than those of a solid. But beyond that, you cannot compress a liquid, okay, which has got a wide range of applications in terms of, technology, right? Furthermore, if we look at the properties of a liquid, we also want to appreciate that the movement of particles is random. So when we say there is random movement, we're saying it is haphazard. There is no sense of order in which these particles are actually moved. But this movement is kind of restricted. Why is it restricted? Because there are slightly stronger forces that exist between the particles of a liquid as they slide past each other, which explains why the liquid will actually take the shape of a container, okay? And then also, with respect to the properties of a liquid, we're saying that collisions between these particles results in the pressure of liquid, okay? So remember, particles of any form of nature of matter are actually, in a constant state of random motion. So the pressure that results from a liquid is, due to these particles colliding with each other and the walls of the container. So that's why, pressure in a liquid is actually in all directions because the movement of these particles is quite random, okay? Right. Let's look at a gas, okay, which is the third state of matter, okay? Also in a gas, these particles, the gas, substances consist of minute particles, which is consistent with also solids as well as liquid. However, there are huge spaces between the particles, and hence these particles are free to move. So the extent of movement of particles is also influenced by how strong the forces that exist between the particles are. So if the forces are generally weaker, it means movement becomes easier. So the amount of kinetic energy that these particles have due to these weak forces would be, by comparison, be much greater. So we need also to pay careful attention to that. So we link what we can observe, remember the air freshener example, in terms of diffusion, these particles moving from a region of low concentration to a region of high concentration. That is only possible, for us to observe the smell, after a couple of seconds. It says that, the extent or the amount of energy that these particles actually possess is, by comparison, much greater, right? So there's also a lot of available spaces. Okay, that's as far as a gas. And also, the movement of these particles is still random, okay? Due to the weak forces, we've managed to link that. And there are slightly stronger forces as particles slide over each other, but this is with respect to a liquid. But also, we want to know that the pressure of a gas is due to how fast these particles are moving and how frequent they collide with the walls of the container. So if, for argument's sake, we trap a fixed mass of a gas, in a container, the pressure of that sample of a gas will entirely depend on how fast these particles are randomly moving, and also how frequent they collide with each other, as well as the walls of the container. Bearing in mind that the collisions between these particles as they move random, does not result in the loss of energy. So, at a point where a sample of a gas has got a greater amount of average kinetic energy, we'd have a situation where the pressure is greater. We'll try and use a simulation just to try and, bring some form of understanding, as to what exactly happens, at a particular level, right? Okay, now we'll go to that simulation to look at what exactly happens, when you talk about the energy involving, the particles of a substance and energy change. Okay, so now if we focus our attention on the simulation to try and understand, as to what exactly happens, between the three states of matter. So we've got, in this case, we've chosen it could be any substance, argon, for example, which consists of those particles that make up that matter. Okay, so we can choose to even add more particles into that container, right? But in this case, it exists as a solid. Okay. Now, what happens if we provide more energy to these particles? They start to move, and we realize that the movement of these particles is quite haphazard. It's random, and by all means, we also appreciate the fact that these particles, they consist of randomly moving units, and they fill all the spaces available. And you can also relate that the pressure as we hit the fixed mass of a gas in this case, what happens, the pressure increases, and pressure is precisely due to how frequent these particles collide with the walls of the container and amongst themselves. Okay, so this is basically just an overview of what happens, at a particular level when you talk about properties, say, of a gaseous type of a material, right? Okay, so going back to our concept, we also want to look into some of the most important aspects in terms of the behavior of matter. But let's keep in mind the big question to say, what evidence does diffusion, the primary motion, provide in terms of the fact that matter consists of particles, okay, and again that these particles are in a constant state of motion. So we want to describe the behavior of matter using the kinetic molecular theory and try to understand exactly why do we observe things that we observe in real life. We've spoken about mixing milk and water. We find out that, okay, there is that movement of particles, meaning that there are spaces that are available between the particles, and the particles themselves are in a constant state of motion. Let's take a short break for now. When we come back, we'll look into more aspects which relate to temperature in as far as the kinetic molecular theory. Let's go for our break now. Welcome back to our third and final segment. We're still exploring the kinetic molecular theory, but we also want to try and link the evidence that is brought forward by diffusion as well as Brownian motion in terms of describing, the particle nature of matter, right? Having said that, the kinetic molecular theory, as a model, it generally gives us a description of the three states of matter at a microscopic level, as we would have seen in the second segment when we looked at the simulation involving a fixed mass of a gas heated, saying that, okay, this the form of matter, which was a gas, is composed of particles, okay? And also these particles are actually in a constant state of motion. But now, with respect to the kinetic molecular theory, we can look at it in terms of the distance which actually affects the spaces between the particles. Okay, so the distance or the space between particles is something that is specific to the kinetic molecular theory in terms of the three different states of matter. We can also talk about it in terms of the movement and the amount of energy. So yes, all forms of matter are in a constant state of motion, but depending on the state or the phase in which that substance is found, then there will obviously be the difference to the extent at which these particles move with respect to the kinetic energy. We're saying that the faster the gas particles move, they have got a comparatively greater amount of kinetic energy than a liquid as well as a solid. Okay, we can also talk about the forces that exist between particles. Stronger forces, meaning liquid spaces. Okay, so the strength of the force will obviously affect the distance between the particles. What are we saying in a nutshell? We are saying if, let's say for argument's sake, in a solid, the forces that exist between the particles are very strong compared to those of a liquid and a gas. Now, if the forces are stronger, it means the distance between the particles will also be smaller. So if the distance is smaller, it means that these particles are closely packed, and hence it would relate to a physical property, like we say that solids have got a definite shape. All that is because of the particle nature, the strength of the forces that exist between the particles, which also influences the distance between the particles, the packaging, and then also you can talk of the shape as well. Okay, so compressibility is also related to the amount of space, which is also influenced by the forces. Okay, so all these dimensions of the kinetic molecular theory are actually link each other with each other very well. Okay, but the most exciting one, or the interesting one that I want us to look at more in detail, is the pressure exerted by a substance in as far as the kinetic molecular theory. We are saying that pressure of a liquid, of a solid and a gas, is due to the movement of the particles. Okay, right. So now we want to look at each one of them, in turn, to say, okay, how does pressure arise in a solid, in a liquid, as well as in a gas? Right. Okay. Okay. So pressure, as a physical quantity, is actually force exerted per unit area. So pressure will actually say to us that, okay, we ask ourselves, how much force is exerted on a surface, okay, and how big is that surface area? So if, say, for argument's sake, we can make an example. If you press with the palm of your hand, okay, using whatever force, okay, what happens is there is greater space on which we exert this force, meaning the pressure will be less, because we are saying that if, say, for argument's sake, we use the tip, you use the same force, this will have a comparatively greater pressure because there is a smaller surface area on which the force acts. Hence, we are saying pressure is actually force applied per unit area. Okay, and we'll talk more about pressure at a later stage, but in terms of calculations and whatnot, but it's not our focus for today. Okay, so in solids, to be precise, a solid exerts a downward force on a surface on which it is in contact or it rests. So if, say, for argument's sake, we had a block, okay, so the pressure of this block is actually the force that this block exerts, and this can be due to, let's say the gravitational force pulling this block downwards. It's resting on a surface, and then how big the surface of contact is, it will affect the pressure. So the greater the area of contact on which the block is resting, it would mean that we'll have a lesser pressure. But if there's a smaller area, if we have the same block placed vertically, if we erect it like this, meaning that this area, surface area of contact, is smaller, this would correspond to greater pressure of a solid, okay? So this pressure will remain constant in as far as solids are concerned, right? Okay, what about in liquid substances? Okay, so in liquids, due to these particles sliding past each other, this relates to the kinetic energy of the particles. So always think about the kinetic energy when it comes to the movement of particles, okay? But characteristically, in liquids, we know that these particles are sliding past each other, okay? And the movement is also random, which results in these liquids taking the shape of the container. So the pressure in liquids is actually in all directions. Why? Because the movement of particles is random. So there is random movement of particles, okay? So there is no sense of direction, okay? So the random movement of particles results in the pressure of a liquid in all directions, okay? So as you can see in the illustration there, the pressure on this block inside a liquid is from all the possible directions. Why? Because these particles, as they slide through past each other, that movement is actually random, okay? Right, and then for a gas, okay, we managed to look at the simulation just to show us that, if these particles are moving haphazard or randomly, they move in all directions. And pressure in a gas is actually, it arises as a result of the particles making that substance moving and colliding with each other in the walls of the container. So if we're thinking in terms of kinetic energy, a gas that is compressed at a high temperature suggests that the amount of energy that these particles have for that random movement is actually greater. So at a higher temperature, we're actually experiencing a greater pressure because of, number one, high speed of random movement of particles, and also high frequency of collisions between the particles themselves as well as the walls of the container. Right, so pressure in a gas would actually be thought of in a different way because it has to do with the frequency of collisions. So when we talk about frequency of collisions, it's a very interesting concept. We are asking ourselves how many collisions occur in a given time, on a surface. So if there is a higher frequency of collision between the particles and the walls of the container, then there will be higher pressure. So this is frequency of collisions. It's another angle of which we can use to actually approach this and try to understand exactly what is happening, right? Okay, so temperature is a physical quantity. It's something that we can measure. We would have done that when we did the heating curve, let's say, of water. We try to understand how temperature changes. But what exactly is the idea around, the quantity of temperature? Temperature, does it suggest how hot or cold something is? But we want to relate this to the kinetic molecular theory of matter. Okay, so temperature is a measure of how cold or hot something is, and we use actually a thermometer. So a thermometer is the instrument, okay? So a thermometer is the instrument for measuring temperature, and then temperature in itself is a physical quantity, right? So temperature is the physical quantity, while the thermometer is actually an instrument that is used to measure this quantity. So the common unit, okay, it's not only that, we've got the degrees Celsius, we also have the kelvins. We'll discuss that, as time goes by, right? So that's what temperature is all about. But with respect to the kinetic molecular theory, okay, particles of matter are always in a state of motion. We understand that all forms of matter are in a continuous state of motion, and this state of motion is actually random, okay? Right, because this is what gives rise to pressure in liquids as well as gases, right? But also, the kinetic energy for the particles is not the same. Now, kinetic energy as a quantity, we are saying that we're asking ourselves, how much energy do these particles have for movement? So particles that move faster have got greater kinetic energy than those that are moving slowly. But, you know, in all the three forms or states of matter, particles are in a constant state of motion. So in essence, what are we saying? There are no particles of matter that do not possess any kinetic energy. So all forms of matter, their particles are in a state of motion, but the state of motion will differ. Suppose we have a sample of a substance. Let's say it could be a gas, for argument's sake, and then all these particles are moving random. The speed at which they are moving is not the same. Some have got high kinetic energy, some have got relatively low kinetic energy. But as a result, we are saying that the amount of energy that each one of them carries is actually not the same. Hence, we talk of the average kinetic energy, right? Okay, so what does it say? So the temperature of a substance with respect to the kinetic molecular theory is actually the measure of the average kinetic energy of particles of a substance. Okay, that's the main idea. Right, so the change in the state of matter is something that we've managed to look into, and we agreed that when we hit the particles of a gas or of any substance, what happens is they gain kinetic energy. But some still will have a comparatively greater amount of energy, some lower. But when we talk about the average kinetic energy, it's something that has got a direct relation to the temperature of a substance. Okay, so temperature of a substance is actually directly proportional to the average kinetic energy. Okay, so temperature is directly proportional to the average EK. Okay, EK will be our kinetic energy. So at a higher temperature, the average kinetic energy is also greater, and vice versa, right? So that's the main idea. So when a substance is heated, these particles, they gain more energy, they move even faster. As a result, there's an increase in the average kinetic energy, of which the opposite is true when a substance is cooled, right? So these are the main ideas in as far as the kinetic molecular theory. So what are the three things that we take out from this discussion? Number one, that all particles, all forms of matter rather, they consist of particles. These particles are in a constant state of motion, hence they've got kinetic energy. And the average kinetic energy of particles is an indication of temperature. Those are the three main ideas that we take home based on today's discussion. So that's the time that we have for today, just to go through the kinetic molecular theory. Hopefully it makes a lot of sense, and we can make these very important links, and try to understand exactly what happens at a microscopic level. From myself, Themba Ncube, cheers and bye-bye for now.